Hello, we'll have a short discussion about acidity of substituted phenols. Phenol is a benzene ring with OH group. It is acidic in nature because it can release a proton and forms phenoxide ion. Have a look at this. This is benzene, OH, oxygen 2 lone pairs. When this proton is given out, minus H plus you see, this electron pair is coming onto oxygen, so you can show oxygen with actually two its own pairs as it is. One extra pair is gained. This extra pair is generally shown with a negative sign. This ion is called phenoxide ion. So simple logic, if the phenoxide ion is easily formed, or if the phenoxide ion is stable, the meaning is the proton is coming out easily from the phenol. That means that particular phenol, that particular substituted phenol is more acidic in nature. If the phenol is more acidic in nature, that means it can easily form the phenoxide ion and it can form stable phenoxide ion. Let's have a discussion about this. For example, if we are having O minus group here, this negative charge is coming here, so the structure will be, the resonance structure will be like this. This is double bond O and the negative charge will be at this place. As we know, this is ortho position, this is ortho position. Now if you take one more structure, this negative charge will come at para position. So at ortho and para positions, more negative charge is going to be there. When we are sure about the negative charge in the benzene ring because of the phenoxide ion, electron withdrawing groups are good because they withdraw the electron density, so they stabilize the phenoxide ion. At the same time, electron donating groups like Placi groups and all, they are into this not good. That means they decrease the acidic nature. Electron withdrawing groups increase the acidic nature of phenols. Electron donating groups decreases the acidic nature of phenols. We'll have some discussion about this in detail. One by one points will go. First we will take up, this is phenol. If fluorine is there, you can expect hydrogen bond. Because of this kind of hydrogen bond, this is intramolecular hydrogen bond, the proton cannot be given out easily, so it is less acidic. You cannot expect all halogen cases, but with fluorine, when it is ortho, intramolecular hydrogen bonding is observed, so which makes it less acidic. The same you can consider in OH. If it is with NO2 group, orthonitrophenol, you can expect this one. Similarly in catechol also you can expect between two OH groups. So when intramolecular hydrogen bonding is present, if it has intramolecular hydrogen bond, it is less acidic. The proton is not released easily, less acidic. Coming to some important groups present on phenol. For example, this is the phenol group. Now I am taking NO2 here. OH, NO2 at meta position, OH, NO2 at para position. If you want, you can take even a phenol. Now let's go with the nature of this NO2. NO2 is a minus R group and minus I group. In order to increase the stability of the phenoxide, minus R is good as well as minus I is also good. Minus R is good because negative resonance is good, it can withdraw the electrons, so this is wonderful, and negative inductivity is also good. When resonance and inductive both are working, as we know, resonance is a stronger group. So we'll take up at ortho position, at para position, we can expect resonance more than at meta position. So in meta position, only minus I is working, and at these positions, minus R is working, which is more. So here, if you see all this is having minus R group at right position, minus R group at right position, minus R but not right position. So here minus I is working, I is less effective when you compare with the resonance. Phenol, when you compare with all this, it is less. So when you are taking about the nitro group, the best will be para, than ortho, than meta, than phenol. If NO2 group is at para, it is more acidic. Actually, we expect in ortho because minus I group must be close. So here, little bit practical experimental data gives that ortho is having slightly less acidic than para. The reason is because of the intramolecular hydrogen bonding. Intramolecular hydrogen bonding is the reason for slightly lower value of the ortho. Otherwise, ortho should be best according to minus I. But intramolecular hydrogen bonding is the reason. So para, ortho, meta, then phenol. We'll take up about methyl group. What is the nature of methyl group? It is plus I. Good. Plus I, as it is distance dependent. Let's take that point. It is hyperconjugation effective. Hyperconjugation at ortho and para positions, you can say this is as resonance, also no bond resonance, ortho and para positions only, so not at meta position. We'll have a look at this. OH with methyl, OH with methyl, OH with methyl. So only phenol. This is, we can call all these compounds as cresols: orthocresol, metacresol, and paracresol. This is ortho, this is meta, this is para. First, see what about this methyl group. As we were discussing, methyl is a plus I group and hyperconjugation. Hyperconjugation is not good here because we don't want any electrons. Hyperconjugation provides electrons, so we don't require hyperconjugation. But hyperconjugation is working in these two cases. Hyperconjugation is not here. Plus I also we don't want. Actually, plus I is not required here. So plus I is distance related. So here plus I is more and hyperconjugation is more. Here hyperconjugation is more, plus I is slightly less. Here no hyperconjugation, only plus I is working here. In this case, nothing is working. So this is number one, the best one. After that meta, after that para, then ortho. See about this. Phenol is better here when methyl groups are there. Then meta is better. Then para is better. Then ortho is better. If the group is methyl at ortho, meta, para. The reason is at meta only inductive working. At para and ortho hyperconjugation is working, but at para the inductive nature is less and at ortho inductive nature is more. Inductive is not working here in the increasing order of acidic nature. It is decreasing, so it must be away. Right? So phenol, meta, para and ortho, it is when you are discussing about cresols. Now let's have a look at these molecules. OH, phenol, OH, NO2 group, OH, NO2 group and NO2 group, OH, 3 NO2 groups. This is also NO2 group. Consider this is NO2, NO2 and NO2. Place is not sufficient. Okay. So this is phenol. Here 1 minus R group. Here 2 minus R groups at right position. Here 3 minus R groups at right positions. So obviously this is stronger acid. So the acidic strength, if you take, this will be the regular order. So this is called 2,4 when NO2 group is present here, OH is present here, NO2 is present here, NO2 is present here. This is 1, 2, 3, 4, 5, 6, 2, 4, 6. Second place, fourth place, and sixth place. If three groups are there, nitro groups, trinitrophenol. This compound is called picric acid. Picric acid. Even though there is no COOH group in this compound, COOH group is not there, just it is OH group, phenol is there, but the name is given as picric acid. It is like respect towards this group. That means it is highly acidic in nature. So when more number of NO2 groups are there, that will be more acidic in nature. Then we will take a few more examples related to halogens. This is phenol. This is phenol with a chlorine group, phenol with a bromine group, phenol with a iodine group, and I am taking here one more phenol with a fluorine group. Chlorine, bromine, iodine and fluorine, all these are strongly minus I, weakly plus R. So in all these cases, plus R we don't discuss, we discuss only minus I. Minus I is the important factor. Minus I is good here, and minus I is place dependent and power dependent. Chlorine is stronger minus I than bromine than iodine. But interestingly, fluorine minus I power is more than chlorine. But even though the highest is given for the chlorine, next place is for the bromine, then iodine, then fluorine, then phenol. I give you again: chlorine, then bromine, then iodine, then fluorine, then phenol. Why so? So when these are present on the phenol, it is like this. The reason is very simple. If it is, as we were discussing just now, OH, if it is there, the hydrogen bonding is possible, so it is having lowest value. This is the problem with this fluorine. The remaining cases, chlorine, bromine, iodine, this is based on the minus I effect. Chlorine is having more minus I nature, so it is more than bromine and more than iodine. This is about the regular order. Then look at this OH group, chlorine at this position, chlorine at this position, chlorine at this position. As we were discussing just now, it is close, it is meta, it is para. Chlorine type of groups are only minus I, so which is better? Chlorine, presence of chlorine is good, so this is least in these four, and the best will be for the one which is very close. So number 1, number 2, number 3, and last one is this one. So this is all you are saying on the basis of only minus I. Here no plus R. When halogens are there, consider only minus I effect. Their plus R is almost 0. See one interesting point. This is phenol. Phenol is almost equal to parafluorophenol. Parafluorophenol. This fluorine is having plus R effect, minus I effect. These two are almost equal. Plus R and minus I both are equal. That means minus I is making it stable, plus R is making it unstable. Because of these two effects are same, this parafluorophenol is having equal strength like phenol. Phenol strength and parafluorophenol strengths are same. Have a look at this question. I am giving you different groups. This is phenol. This is phenol with OH group. This is phenol with Cl group. This is phenol with NO2 group. What are their natures and how it is going to work out? When you are taking your OH, this is Cl, this is NO2. This is phenol, no group is present. NO2 is minus R minus I, which is much better. Chlorine is only minus I, no resonance effect is working, only minus I. This is minus R minus I. It is minus I but plus R. Plus R is stronger than minus I, so this is not good for us, and this is only phenol. So the best one is with nitro, this is first, and then chlorine, this is second, then OH group and another OH group. Two OH groups are there, but both these they participate in intermolecular hydrogen bonding, so the protons will be busy. And second thing is the resonance effect is more stronger here, so in these kind of cases the better one is phenol. Phenol is better than two OH groups because both OH groups are participating in hydrogen bonding. So like this we need to explain the what you say acidic nature of the phenols. And for example, if nitro group is present, which will give maximum value, para is the best. After para, nitro group. Nitro group means that must be electron withdrawing group as well as minus R group. So the best one is para, then ortho, then meta. If NO2 group is present on the phenol ring. If NH2 group is present, I take only two options, ortho and meta, which will be better. NH2 is having a lone pair of electrons, so this is plus R effect and minus I effect. Which will be stronger? Definitely plus R effect is stronger. So when plus R effect is stronger here, minus effect is weak here, so ortho will be less and meta will be better, because at meta no resonance factor is not working, only minus I is working, so it will be better. So meta is better than ortho if we are having amine group, NH2 group. If we are having fluorine, if fluorine is present, then ortho, meta and para, if you consider, the values of these will be very interesting. Metafluorophenol, orthofluorophenol and parafluorophenol. In orthofluorophenol, as we were discussing, intramolecular hydrogen bonding will be there. In parafluorophenol also we can expect intermolecular hydrogen bonding. So orthofluorophenol and parafluorophenol, these two. Along with this we have meta. At meta the hydrogen bonding ability is less. And the second thing is it is minus I group. Minus I is position oriented, and plus R group. At meta there is no plus R. That's why meta is better than ortho than para. Meta, ortho, para. If you are considering even the Ka and Pk values also, you will be getting the same thing. And when you consider resorcinol, hydroquinone and catechol, the resorcinol is better than hydroquinone than catechol. The OH groups present at meta position is better than OH group present at 1,4 positions than OH groups present at 1,2 positions. As we know, 1,3 position is called resorcinol, 1,4 position is called hydroquinone, or you say quinol, and this is catechol. The reasons are same, the nature of OH group. So in this way you need to answer all these questions. Sometimes they can ask you Ka and pKa values also. Ka high, pKa low. In these cases you can say these are strong acids. Strong acid means Ka should be more and pK value should be less. Next time we'll discuss about benzoic acid and its derivatives. Have a wonderful time.